So, what are we doing today? That's what we're doing. We're going to classify polygons today. Well, first, we probably need to know what a polygon is. Time for another one of those definitions. Well, there's a definition. And like most definitions, it probably leaves you a little cold, wondering what the heck this is supposed to mean. I think a picture is probably a lot better. 1,000 words and all that. Now let's give it a try. Now remember, in a polygon, for one thing, the lines always... Hold on a minute. The lines are end-to-end. Well, they're line segments, pardon me. You can extend them to form lines. And in fact, for the terms, two more terms we're going to learn in just a minute, we will have to extend the segment into a line. They're not super important terms right now, but we have to learn them because they're there. Sometimes that's the only reason. Let's start with a really simple polygon. And there's a line, and there's a line, and there's, well, a segment. Segment, segment, segment. 3 segments. That's what we call a triangle, isn't it? You could call it a three-gon, but hardly anybody would know what you were talking about. And that's how we name or label these things. For instance, this, what you would normally call a rectangle, well, we could also call it if you were to stick with the n-gon labeling, this would be a 4-gon or quadrigon, but they don't do it that way. The first couple are given much more, well, names that make them sound unique, such as triangle and rectangle, because this is a specific type of what? It has 4 sides, and we call it a quadrilateral, not a 4-gon. It's a quadrilateral. In the polygons with more sides, we use that n-gon terminology, but still not that simple because the first term is hardly ever English. It's not called a 5-gon, it's called a pentagon, and it's not called an 8-gon, it's called an octagon. They just do that to help confuse you. After all, it wouldn't be any fun if you didn't get a little confused, would it? Besides, how could the people who know this stuff look smart if everybody understood it? By saying hexagon, people can scratch their head and say, oh, what the heck's that? Well, those of us who know that hex just means 6. So, a hexagon, well, in English that's just a 6-gon. So why don't they just say 6-gon? I don't know. Probably because they wouldn't look so smart if they said 6-gon. So we're going to have to say hexagon, and on down the line. In fact, we're going to classify a whole bunch of them. We'll see a lot more of them later. For now, you just need to understand that a polygon, number 1, it's all in one plane. It's not allowed to bend outwards into another plane. You may have seen, when you take like a piece of paper that's rectangular. If it's lying flat on your table, it represents a polygon. But if you pick it up and start twisting it around, it's not a polygon anymore because it's not lying in one plane. Now, here's some terms they introduce. Concave and convex. This would be what you call convex. And why is that? That's just a word they used to decide whether, if you were to extend these segments into lines, would they cross the interior of this object, or would they always be on the outside of the object? This is interior, this is exterior. So would they be interior or exterior? Well, you might be thinking, that's kind of a dumb question. Of course they're interior. Well, if you draw it this way, it is. And most of the polygons that you would tend to think of would be convex, but suppose I drew it this way. Now, if I extend these lines, this line, or this line, I would still be inclined to say that it's convex. But if I extend this line, that goes into the interior. That makes it concave. And that's about all you have to know about this. Just look at the lines that form the sides. That's what these are each called. That's a side, 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 side. All these straight line segments are called sides. If you can extend the side into a line, and it extends into the interior of the polygon, then it's concave. If not, it's convex. I checked a couple of state exams to see if I could even find the words concave and convex. And to tell you the truth, the standardized exams that I found didn't even ask any questions about them. But you never know, they could change that. You may find a test with, say, one question on it, so it's good to know what the heck this means. That's a real easy way to remember it. Just extend the sides. If any of them would extend out into the interior, it's concave. If not, it's convex. There's another way to look at polygons as to whether their sides are all equal. Equilateral. Side. Equal sides. That's what it means. Normally, this word is used for triangles. Technically, you can have an equilateral octagon, but probably an equilateral octagon would turn out to be a regular octagon. Equiangular, that's a word you don't hear very often at all, but you might as well know what it means because it'll crop up in problems. They'll present a problem, and part of the given information is that the polygon is equiangular, and you will use that. And so it behooves you to know that equiangular means equal angles. You would probably know that even if I didn't tell you. Regular, that's a little bit different. That incorporates both of these, really. This one just means that this is both true. They have equal sides and equal angles. Now, it doesn't have to be that way. I mean, you can have sides that are all equal. For instance, if I drew I don't know if I can draw one, like a diamond, say. So let's say that side's equal to this one, and that these two sides are both equal. Boy, if I could draw, I'd be kind of a dangerous person. There we go. And now, humor me. Pretend that each one of these sides is equal, and I'll do it this way, so you don't even have to know that that's what I intended. When I do that, remember, we learned last time, we put like one hash mark on each one. That means they're all the same. If I drew two here and then two here, that would mean these two are the same, but the way it's written. All four sides are equal, but the angles are not. That's a real big angle. In fact, that's obtuse, and this is acute. Obtuse, greater than 90 degrees. Acute, less than 90 degrees. So it could be equilateral and not equiangular. In order to be regular, well, in the case of four sides, each would have to be 90 degrees. That's not hard to figure out because we're all familiar with squares. And each one of these is a right angle, of course. So a regular polygon includes both of these. And it's important that you know that because you will be working frequently with regular polygons and making use of the properties of regular polygons, which is that they have equal sides, like this, but they also have equal angles at each vertex. Where these sides come together, that's called a vertex. It's not a vertex if two opposite lines. Say, let's suppose we had two opposite rays. There's a ray that goes that way. Wow, bad. Okay, there we go. And there's a ray that goes that way. And here's the vertex. No, we don't get to call that a vertex. Wrong. If it forms a straight line, it's not a vertex. And we're not going to get very interesting polygons if we keep adding them endpoints in straight lines. We're just going to end up with a bunch of lines put together. Okay, now with these 6 polygons, we're going to classify them by the number of sides, whether they're equilateral, equiangular, or regular. So let's start with this one here. What have we got? 1, 2, 3, 4 over here. 5, 6, 7, 8. Well, if I counted right, we've got an octagon. I guess that's right. We got 3 sides over here, 3 here, and then 2 right there. So that's 8, and there's an octagon. So if I didn't already know it was an octagon, I could have looked at the table over here. I stuck this here over on the side, so you can refer to it as we're going through these real quick here. Octagon. Now, is it equilateral? You know, earlier I said equilateral is used more often. Well, forget it. I think it's more often used for triangles. It isn't used that often in polygons, but it does apply to polygons. So all I'm going to do is confuse you if I get too deep into this. Let's just say this is certainly equilateral. Why? How do we know that? Well, you're not supposed to go by just how things look, because how would you know if it was 1/100th of an inch off? And if it's 1/100th of an inch off, technically it's not equilateral. Well, you know because of these hash marks they put here. There's one on each one to indicate that every side is the same. So now we know because of these hash marks, and that's the only reason we know, it's equilateral. Is it equiangular? In other words, are all the angles equal? I think it's easier to say all the angles are equal than it is to say equiangular. Oh well. Now these little arcs, if it's a single arc, that means everything with a single arc is congruent. Well, they all have the same single arc, so they must all be congruent, so it is equiangular. If it's equilateral and equiangular, what is it? It's regular. In fact, I tend to think of a regular polygon as one in which all the sides are equal and all the angles are equal. You just think of it that way, it seems a little simpler than throwing all these big words around. Well, what about this one here? Is it equiangular? Well, these two angles are indicated as being equal, but not this one, and they all have to be equal to be equiangular. So the answer is no. Is it equilateral? Well, they tell you right here. This is 5 meters, and 4. 2 of the sides are the same, but this one isn't. And to give you a little preview of what's coming up, when 2 sides are equal, that's actually called an isosceles triangle. But you don't need to know that yet. We'll get to that when we study more triangles. But actually, you probably know it's called an isosceles triangle from other classes. What about this one here? Well, we got 2, 3, 4, 5 sides. And by the way, this one had 3 sides and was a triangle. I forgot to mention it. I doubt if there's anybody in the room who didn't know that instantly, even before you took this class. 5 sides here, that's a pentagon. Is it equilateral? Well, instead of using hash marks, they actually labeled the length of each side, and each side is 1 inch. So yes, every side is equal, so it's equilateral. The angles, yep, they drew the little arcs in there again to show you that each angle is equal, so it's equiangular. That means it's regular. Here's one, a lot similar to the example I drew to show that they don't have to be equiangular even though they're equilateral. Here we got the little hash mark to show us that each side is equal, it's equilateral, but you can probably tell even without the hash marks that these angles aren't equal, but they drew in the little arcs here so that you can see for sure this angle and this angle are not equal. So it's not equiangular, and therefore it's not regular either. It is equilateral, and that's all. This is also called a quadrilateral. You don't get to the gons until you get up to 5 sides. First you get the triangle, then the quadrilateral, and the n-gons is usually 5 sides and more. Here, triangle, of course. All the sides are equal, and all the angles are equal. That means it's equilateral, equiangular. It is regular, but we have a special word for a regular triangle. We usually call it an equilateral triangle. There's a reason that we can say an equilateral triangle and nothing more. Because for triangles, and only triangles, if all the sides are equal, then all the angles have to be equal too. We'll prove that later on. But that's why it's okay to call this equilateral and not even talk about the angles, because they just come right along with it. It's like a package deal. If the sides are equal, then the angles have to be equal. That's only true for triangles. Don't confuse that with any other polygon. Triangles are kind of special. What do we have down here? Well, we have these marks here which show us that each one of these is a right angle. So it's equiangular. But we have these little hash marks to tell us that these two sides aren't the same. So it's not equilateral, and it's not regular. Okay, and here's a nice quick one that help you avoid the errors that others have made. And they always list it as 2 students, and they show the error that students made. I don't know why it has to be a student. I mean, 2 English teachers might have done this. You never know. They don't study math that much. 2 people standing at a bus stop may have been asked this question. They might have made that mistake too. I don't know why they're always ragging on students like they're the ones making all the mistakes. What's wrong with this one here? Well, the student, you know, those people who are always making mistakes, all the sides are equal. So he drew an equilateral hexagon. But these angles don't look equal to me. Look at that one. That one's huge. That one's tiny. I mean, you don't have to be, oh yeah, look at that angle in there. That one's really big, right? That's more than 180 degrees. That is wrong, because the angles all have to be the same to be regular. It's not just enough that the sides be equal. The angles have to be congruent as well. Over here, what did this person do wrong? Well, the angles are all equal. They got that right, or congruent if you prefer. However, are the side lengths equal? Nope. So we got that part wrong. So each one of these students got half of the definition right. They just left out the other half. That's all. Now in here, it's given that this is a regular polygon, which in this case, of course, would be a square. The question is to find x. So we're going to be doing what we've done all along. We're going to make use of the fact this is a regular polygon. What does that mean? Well, it means a couple of things. All the angles are equal, and all the sides are equal. Pardon me. The measure of all the angles is equal, and the measure of all the line segments is equal. So let's make use of that. X squared plus x equals x squared plus 4. So we're going to end up with a polynomial, aren't we? We're going to get 2x squared. You can set it up in kind of a... Of course we're not going to get 2x squared. That's my first dumb mistake today, if you're counting. There may be more. We just subtract x squared from each side and get that x equals 4. pardon my space out there. I think I've mentioned before, I do this in my head a lot, just like you shouldn't, and I hope to demonstrate why you shouldn't do things in your head, especially not on a test. An assignment, what the heck, you'll probably spot the error and you go back and fix it. It's another reason why you should always check your work, because if I had continued with my mistake, I would not have gotten that these two sides were equal. But if I punch 4 back in here, what do I get? 16 plus 4? Yeah, that's 20. 16 plus 4, well, that's 20. So, it works. Now, here's an interesting one where we're going to have to use some of what we learned in this section. And we're going to have to go back and remember some of the things we learned before, such as supplementary angles or linear pairs. Maybe the first thing we should do now, those of you who already know some geometry may be thinking, we already know what the angles are in a pentagon, but we haven't gotten to that yet. We haven't actually proved what the measure of each angle is going to be. All we know so far is that this is a regular pentagon, and since it's regular, the sides are all equal, and the angles are all equal. So down here, where they're apparently giving you the measure of two different angles, they're not even telling you which angles they are. But that's okay, because all the angles have the same measure. So we're going to compute the angle of a pentagon the hard way, because we don't know what it is yet. We haven't learned that. But we know they're all equal. So when I say pentagon, I meant regular pentagon. Pardon me. Since they're all equal, we can set up this equation. That's 33x. Whoa. So what do we get? Well, we can have 13x here. That's 33x minus 20, and 48 minus 9 is 39. Well, that's convenient, because 39 happens to be divisible by 13, and it equals, so x equals 3. So we should be able to plug that into either one of these. That's 60 plus 48. So each of these angles here equals, that's the measure of the angle, and it could be any angle. I didn't bother to specify, because they're all the same. Would be 108, at least if you use this equation. Let's see if we got it right. That's 99 plus 9, well, that's 108 also. So each one of these angles here is 108 degrees. Now we could find angle BCA, couldn't we? Because BCA and this angle here, whatever we call that, let's call this alpha 1. Well, that forms a linear pair, so we know that alpha 1 plus the measure of angle BCA equals 108 plus the measure of angle BCA, and that equals 180. It's a linear pair. So if we subtract 108 from 180, we get 72, and that is the measure of angle. It's supposed to be a B. It looks a lot like an R, doesn't it? B, C, A. So that's that angle right there. What about this angle here? Well, I think we can apply the linearity theorem again. linearity property again, because this angle here and this angle, these two right here, these form a linear pair. And this is 108. Remember, these are all the same pentagon. It's just reproduced over and over, so they're all exactly the same size. And they're considered exactly the same. They're all regular, of course. Which means this angle must be 180 minus 108 also. So this one is 72 degrees. So we have two angles that are 72 degrees. And there are some things we don't know yet that we could make use of, but we're going to do this using only what we know so far. So this angle here, we know that's 72 degrees. Like that. This angle here, we know it's 72 degrees. Again, because the same linear pair relationship. Now what about these two angles here? Well, they drew these lines in here. They did us a favor. If we call that, each of these two angles, say alpha 2, well, we have 1, 2, 3 angles that make up a straight line. So they're supplemental. So this plus this plus this. These two are equal though. So when we set up our equation, if we call this alpha 2, then this would be 2 alpha 2 plus the 108. Remember, these all have the same angle. Plus 108 equals 180. That's going to give us the 2 alpha 2 equals 72. So each one of these angles here must be 36 degrees. We made use of the fact that every angle in a regular pentagon is equal, or congruent. The measure of each angle is equal. And we made use of linear pairs and a supplemental set of triangles. So we used the regular property, we used supplemental property, and linear pairs. And as you can see, when you put it all together, it actually leads to fairly simple equations and pretty easy answers. And here we have one that's going to require a coordinate plane. Well, luckily we have one. Two vertices of a regular quadrilateral are A04. Well, okay, let's put that right there. There's A. And B, 0. Well, there's B. 0 minus 4. Which of the following could be the other two vertices? Well, this isn't so bad if we remember a few things. Remember, regular quadrilateral. Quadrilateral, 4 sides. Regular, all the sides are equal and all the angles are equal. And as you've seen in previous problems, the regular quadrilateral is going to be a square. As all 4 sides are the same, well, it's supposed to be a square, pardon me. And they're all right angles here. If this is the vertex, we need 2 lines that intersect at right angles. We also need 2 lines that intersect at right angles over here, because this is another vertex. And we could do this. Those intersect at right angles. But what are we going to do with this one? It's not going to work out very well. That's not really a good idea. Suppose we did it this way. With our y-axis as a bisector of a 90-degree angle, like that. And then we did the same thing here. 90 degrees to be 45 off of the axis here. Just going to take a shot at sketching in 45 degrees. Try that. Now, let's see here. Now this so-called line here I drew so badly, I redrew it as a straight line at a 45-degree angle off the axis and 45 here. And as we know from the previous section, these two will add up to the total angle, which is 90 degrees. So it looks to me like we've just reversed the other two endpoints. And I would say that the other endpoints were 4, 0 and minus 4, 0. Is that answer up there anywhere? And of course, that answer isn't up there. Why not? There's more than one way for these 2 points to be the vertices of a regular quadrilateral. That's why it says which could be. I drew one thinking that what seemed the most obvious to me would be the obvious one to them. Well, it's not. There's another one in there. So we could take another approach to this problem. See, we'll get rid of what we've done so far, or most of it. So let's take a different approach to this problem. Instead of drawing the first quadrilateral that occurs to you, like I did, let's take a look at the various points and see if they make any sense. That would be another way to do it. What about the point 4, 4? Well, let's see here. We got 4, 4 here. Pardon me, that's minus. Well, gee whiz. Here's the point 4, 4 over here. Right here. Minus 4, 4. That's over here. I don't really see how we're going to connect those up into a quadrilateral. What about minus 4, 4? Well, that would be this one again here. And minus 4, minus 4. Well, that would come close. That'll give us a quadrilateral. But it won't be a regular quadrilateral, will it? So that won't work. What about 8 minus 4? There's 8. And there's minus 4. Hey, we'll not be onto something here. Because this is going to have a length of 8. And this is going to have a length of 8. But let's double check. And 8, 4. 8, 4. So, this one is just straight up and down with the middle right here. We take that line and just basically move it over 8 units. And we have another regular quadrilateral, which we can draw in even more easily than the one I tried to draw. This is a nice simple. So this would be it right here. Now here's a problem which borders on the practical. Suppose you were manufacturing things and actually needed to know. When you're ordering, you're going to make, say, 10,000 of these little things. You need to know how much silver wire to order. Well, here's what you can do. Although you probably wouldn't have to set up an algebraic equation if you were actually doing that. But the part after the algebraic equation is actually very practical. So, it's a regular polygon. That means every side is equal, which means this equals this. All we have to do is set it up that way. 3x plus 12 equals 20 minus 5x. So we get 8x equals 8, or x equals 1. Now let's check our answer. 3 plus 12, that's 15. 20 minus 5, well, that's 15 also. So we're good. X equals 1. Side equals 15, but how many sides do we have here? Well, there's 3 there, and we have 7. And what is that called? That's a septagon, I believe. No, it's a heptagon. Pardon me. Yeah, it's a heptagon. I got the hep right. I think a septagon is actually 9 sides. Sorry. Pentagon. That's 7 sides. So how much silver wire do you need? The question is, how many millimeters of silver wire do you need? Well, it's just 7 times 15. Boom. Well, that's it for now. This is all pretty simple stuff. We're going to use it in later sections.